This is question number 7 from the SACE Stage 2 Physics course companion from Subtopic 2.5 Electromagnetic Induction. Here we have a square loop with a uniform entering a uniform magnetic field directed out of the page with a side length of 12 centimeters. The magnetic field has a magnitude of 5.8 millitesla and it enters into the field in a time of 1.4 milliseconds. First, we need to work out the change in magnetic flux through the square loop. So here we're trying to work out change in magnetic flux, which we know is equal to the change in magnetic field times perpendicular area. Now here it's the area which is changing, not the magnetic field. So it might be easier to write this as B times change in perpendicular area. Now it's just a matter of substituting the values that we have in the question. So the magnetic field is 5.8 millitesla. So making sure that conversion is correct, and the change in area is going from not being in the field to completely immersed within the field, so it just ends up being the area of the square, making sure we convert the 12 centimeters to meters. So 0.12 multiplied by 0.12, and substituting that into the calculator gives 8.35 times 10 to the minus 5 Weber. That's question A. Now we have to work out the magnitude of the induced EMF in a loop. So here we're just using Faraday's law. So EMF equals N change in flux over change in time. Here we just got one loop, so N will be 1. The change in flux we've just calculated, 8.35 times 10 to the power of minus 5 Weber, and the change in time from the question was 1.4 milliseconds. And substituting that into the calculator gives 5.97 times 10 to the power of minus 2 volts. Now we have to work out the direction of the induced current in the loop. This is probably the most difficult, so it's best to talk through this using Lenz's law. So here we have the magnetic flux is increasing as it enters the field, so I find it easier to write this as change in flux is increasing and it's directed out of the page. Therefore, from Lenz's law, the magnetic field due to the induced current needs to be directed into the page. So if we're using our right-hand rule now to determine the direction of the current which will produce a magnetic field that's directed into the page, then that will be clockwise. So here we go, I is clockwise. Yeah, so it might be helpful to draw a diagram of that. So here we have the loop, we have the magnetic field, the external magnetic field is out of the page, therefore the induced magnetic field, since the flux is increasing to oppose that change in flux, we need a magnetic field directed into the page like this. Therefore, by the right-hand rule, the current needs to be going this way. So Lenz's law is probably the most difficult part of this, but the rest of it's fairly straightforward.